Hi, I'm Frank David from Pharmagellan, a biotech consulting firm. This video is the fourth and last installment in a series on how to interpret time-to-event studies and Kaplan-Meier curves. In this episode, we'll cover some classic red flags that you'll see in journal articles, drug companies' presentations, and investor decks. As a reminder, we're talking in this series about studies that measure the likelihood that a patient will experience an event like death or hospitalization over time when treated with a drug versus a control therapy. You've probably seen classic staircase graphs like these at medical meetings or in companies' presentations to investors. Like with any study, there are a slew of things you want to note about a time-to-event study's design, execution, and results. I won't cover all of them here, but instead I'll focus on what I think are the three main places where it's easy to get misled when you read results from these sorts of trials. Before we get started, two quick notes. First, you don't need to be an expert in statistics or trial design to get something out of this video. You just need to have some experience reading reports of biotech clinical studies in journals, medical meetings, and press releases. And if you're just jumping in, you should probably check out the links below to the earlier three videos in this series, which introduced how these studies are done and the main numerical and graphical outputs. Second, if you find these videos useful, you may also like our free white paper on interpreting biotech trial results and our detailed book for non-statisticians on analyzing all aspects of biotech studies. Links are in the notes below. So, in this video, I'm going to cover three red flags you should watch out for when you read a report from a time-to-event study. Those have to do with the definition of an event, the magnitude of the effect, and the graphs. Let's start with how an event is defined. This may seem trivial because in every trial, you need to make sure you know what the primary endpoint is. But it can be particularly tricky in time-to-event studies because often the definition is buried in the methods and not obvious from the press release or the figure. This issue came up in some studies of COVID-19 drugs for hospitalized patients. The successful phase 3 ACTT1 study of remdesivir and a failed phase 3 study of sarilumab both used recovery as their endpoints. But one defined recovery as 1 to 3 on an 8-point scale, while the other scored it as 1 to 2 on a 7-point scale. This kind of thing can happen, especially in areas that are relatively new for drug development, including many rare diseases, and it makes it really hard to interpret the results. A related source of confusion in time-to-event studies has to do with composite endpoints. That's when the trial defines a set of clinically important outcomes and any one of them counts as an event. For example, many cardiology studies count any instance of cardiovascular death, non-fatal heart attack, or non-fatal stroke as an event. This definition is actually pretty well established in drug development for cardiovascular disease. But in other indications, like pulmonary arterial hypertension or blood cancers requiring allogeneic hematopoietic stem cell transplants, drug studies have used various definitions of clinical worsening, each with different components. So even in an area you think you know well, if you're reading a time-to-event trial, make sure that you check that the definition of an event is what you think it is. Second, it's particularly important in time-to-event studies to watch out for statistically significant results that are clinically pretty insignificant. That is especially important here because of how the results are presented. As we talked about in the second episode of this series, a hazard ratio below 1 and a p-value of less than 0.05 mean the study was successful, but they don't tell you much about the actual effect on patients. That means there are many cases in which companies trumpet statistically positive results from time-to-event studies when the absolute improvement isn't very meaningful. A classic example of this is an old study of erlotinib plus gemcitabine versus gemcitabine alone in metastatic pancreatic cancer. On first glance, a hazard ratio of 0.82 with a p-value of 0.038 doesn't look so bad. But on an absolute level, the overall survival gain from adding erlotinib is only about 10 days, which is pretty minuscule. Although the study was technically positive, it's hard to imagine regulators, payers, patients, or doctors being impressed with that small a benefit, no matter what the p-value says. Third, as we discussed in the prior episode on time-to-event figures, you need to be on the lookout for odd features in the graphs from these studies. I'm specifically talking here about strange censoring patterns, late or no curve divergence, and crossing curves. None of these are gotcha findings that would make you call the entire study invalid, but they should make you take a step back and dig into why the graph has this weird feature. Let's quickly go through a few examples. Lots of early censoring in one arm isn't very common, but if you see it, it should raise alarms. In this academic trial of S1 chemotherapy plus either oxaliplatin or cisplatin in gastric cancer, the high amount of early censoring in the oxaliplatin arm is definitely odd. From the paper, it seems like these patients had a much higher incidence of hematologic side effects that may have caused them to withdraw early. That doesn't mean the entire study is invalid, but it does tell you that there's something else going on that's worth investigating and might affect how you interpret the results. By far, the most common red flag you'll see in time to event figures is late divergence. As mentioned in episode 3 of this series, you shouldn't get very excited when curves separate toward the right-hand side of a time to event graph because the error bars around these points are huge, so any difference you see there is often a red herring. In this study of neratinib versus lapatinib in HER2-positive breast cancer, most of the separation between the two lines occurs late, after 40 months or so. As discussed in episode 3, a good rule of thumb is to draw an imaginary vertical line where 20% of the study patients remain at risk, which in this case would be around 27 months. At that time point, the curves are essentially overlapping, which should make you cautious about calling this a positive result regardless of the stats. Finally, as we talked about in the last video, when the curves cross in a time to event graph, it indicates that the constant proportional hazards assumption has been violated, which can call the math into question. Most of the examples of curve crossing you'll see are for immuno-oncology agents, like the Keytruda study shown here, where there's a good biological rationale for why it happened. In this case, it's likely that chemotherapy starts killing cancer cells almost immediately, while immune drugs like Keytruda take more time to have an effect. That's why chemo looks superior for the first few months of the trial, but then the curves cross and Keytruda is clearly better overall in the long run. In general, curve crossing toward the left-hand side of the figure, like in Keynote 45, is much less concerning, especially if there's a plausible explanation for it. But if it happens late or is hard to explain, then that should set off alarm bells. To wrap up, let's review the main red flags in time to event studies that we discussed here. First, make sure you know exactly how an event was defined so you can interpret the findings and put them in context with other studies in the same clinical area. Second, even if the hazard ratio and p-value look good, make sure you check out the absolute magnitude of the drug's effect to see if it's clinically significant. And finally, be on the lookout for a few classic oddities in the graphs that accompany time to event studies, including unequal and early censoring, late divergence, and crossing curves. These aren't necessarily deal breakers, but you should dig into them if you see them. Well, that's it for the final episode in this 4-part series on time to event studies and Kaplan-Meier curves. If you've stuck with me until now and still want to learn more about biotech trials, please check out our white paper on interpreting study results and our comprehensive book on analyzing all of the components of biotech studies. Details are in the notes and at pharmagellan.com. Thanks for watching.